Okay, yep. So today we're going to talk about filters, continue our discussion on filters. Close this guy. All right, so specifically we want to understand filters from the perspective of both spatial and frequency domain. All right, so first of all, yes. The slide link should be there. Let me see. Sorry. Give me a second. Since many of the slides are too big, so I couldn't really upload them, but I provide the link. Let me see if I can find the link. All right, so if you go to these link here, so you should be able to see these things, okay? And you'll be able to download this. Okay, does that make sense? Maybe I should post this again. Let me post this again in the chat. Yeah, so you see, like, go to your LMS, you will be able to see this. Can you find it? Okay. All right. Okay, so very quick recap of what we talked about last time, that you have an image, and images are basically multiple channels, just like Homo 1, you have multiple channels, you want to merge them together, kind of align them together to give final image. Okay, so this is something that we want. Okay, so and then the specific problem we're dealing with is this, right? So you have an input image, and then you want to be able to do operation on top of this input image, right? These input images are just 2D array of numbers, right? So one important tool for processing these images is called filters, okay? So what it does, like a simplest filter, looks like this. So you have a specific kernel that's a local window specify what's the coefficient you're going to do to linearly combine the input values. Okay, so you have this this very simple kernel is just doing some weighted, doing some averaging over the pixel values. So the effect we talked about last time is just that you will get something a blur. Okay, so you go through this process for every pixel, you get something that's blurry. Okay, in the end, you get something like on the left hand side is a sharper image, on the right hand side is a blur image. Okay, so but it's not just for this simple blur kernel, right? So if you specify the numbers within this window, you get a variety of different functions. Okay, let me show you what that function looks like with different kernels. Okay, so let me find this interactive window. Okay, so imagine you have a blur kernel. So this. Okay, so the simplest kernel is just everything where 0 and it's 1 in the center. Okay, what a kernel is that if you look at my mouse here is specify where do you want to extract the data, and you take the data, there's the intensity, and then multiply by this. So this is a trivial kernel, right? Because it's just doing nothing, the identity. Okay, but now if you start to say you have a blur kernel, that this guy, what does is that you take any window and then you take a weighted average of the 0.2 of the center values and then surrounding values. These are the Gaussian kernel. If you take this kernel, you'll see that on the right hand side you get something blurry. Okay, yes. Oh, really? Oh, sorry. Let me see if I let me correct that. Okay, maybe the link is wrong. Okay, give me that. Okay, now it should work. Okay, try again. Where am I? Okay. So where's my mouse? Okay, I'm here. All right. So now you have this kind of the operation, right? So and you can do some other things. For example, if you specify the kernel to be say leftover, okay? What it does is that you will take the 1, 2, 1 on the left hand side and -1, -2, -1 at right hand side. So basically kind of doing some weighted average on the pixel to the left minus the pixel to the right. So what is this trying to do is to identify where the kind of this vertical line is, right? If there is a large value from the left hand side and the lower value on the right hand side, and then you will detect these vertical edges. Okay, so this is a kind of great tool for the analyzing the images. Okay, so for example, you have this, and you see that you'll see the response is that it's trying to detect certain features. Okay, so if you do the other ones, and you can also do, okay, so top shuffle is like if you do the other way around, so you are trying to detect the horizontal structures. Okay. All right. So you could also do something like you can also do this for once you have the blur and you take the image and subtract to the blur, that becomes the details, right? Because the image is full of details and you remove the blur regions, then you have some details. And you can add the detail bags, right? So here you can see that now you have something that can sharpen an image, right? Given it's simple image, you can sharpen the details of an image. All right. So you can see that there are multiple different ways of doing different things. And yeah, so and you can change all these kind of filters as however you want. Okay. And you will see different effects of this. All right. So when people talk about convolutional neural networks, basically they're trying to learn instead of just one filter, they're trying from multiple different filters and multiple different layers. And the way that but fundamentally what you can think about these filters is to detect patterns, right? Detect certain patterns, and combination of these patterns result in certain semantic concepts. Okay. All right. So that's why we want to study image filters. All right, so let me move this away. Okay, so last time we talked about like one thing you can do is to do blur, right? And if you can increase the size of kernel, you get more and more blur, right? So this is pretty obvious. And then there are multiple ways we can handle the boundary. Okay, so we have talked about this last time. Okay. But the problem is that this blur kernel, box blur, is actually doing a lousy job at blurring the image content, right? So it's not really perform what we intended to do, like removing these high frequency details. Okay, so then we talk about like, okay, we can make the blur kernel more smooth by saying that okay, use a smooth weight, like a center still high, then the lower gradually decay these weights. Okay, and now we see that it's much better. If you see the Gaussian kernel, it's still you can increase the blur kernel by increasing the like how the standard deviation of the Gaussian kernel, then you get a more and more blur image. Okay, so this is great. Now you have a very effective way of removing details. But the question is why the box blur is bad and Gaussian blur is better. Okay, why is that it can deal with this? To understand this, we really need to understand the convolution and the frequency perspective of what this blur kernel blur filter is actually doing. Okay, so so we talked about this last time. We basically think about study this this frequency this operations of this blur operations as a signal and apply a system on top of that to get another signal. Okay, so this is, you can think about this 1D signal is just a scan line of the intensity of these images. Okay, so let's study the 1D signal. All right, so we talk about this filter operation, basically local weighted average operation, can be described by this system. Okay, and that particular system has two properties. That's one, linearity, the other is shift invariance. Yes.
You think that what's on this right now is like how does this represent?
So I haven't said that the kernel yet. So this on the left hand side and right hand side, you can imagine that this is the intensity profile of a scan line of the image. Okay. Yeah. So every pixel and every pixel has different values, right? Make sense? All right. And then we're saying that with the filter is basically a machine that feeding some input and spit out some output. Okay. And that we are trying to understand the mathematical foundation of a filter, like why we can specify this filter with just these kernels. Yes.
And like just to clarify that, because like this has some values and it's transformed over heights.
Yeah, this filter is doing some kind of blurring. Okay. All right. So, and specifically, you want to understand that if this, in general, the system could be very, very complex, right? It could be doing some nonlinear stuff. But for linear and shift invariant, if the system has this linear and shift invariant property, we can specify, we can completely describe the system by a blur kernel, by a kernel that's weight. All right, so why is that the case? If you look at this, and we talked about this last time, linearity basically means that if you scale the input, you get the same output scaled. And you can also think about if if you decompose this input into multiple different, if you decompose this input, feed into the system, and then your predictions of this output is the same as this output, separate output, add them out together. So this is called linearity. Okay. All right, and then we have the shift invariance. That is says that if you have a signal, and then if you shifted the signal, input signal, the output signal will just be shifted. Okay. So with these two property, this type of thing, if any system has these two property, it means that you can describe the system by just a filter. Okay. That's basically what it is. And that has a beautiful connection with the Fourier transform later on. Okay, so now we have the reason why we want to have this is that any signal can be decomposed into a collection of impulse response, right? The impulse response, any signal any image can be described by like a pixel 1 has this value, pixel 2 has this value, and so on. So this is trivial representation. And then if you feed into the system, you'll get some output, okay? You'll get some output, right? And the idea is that this is where the shift invariance comes in, right? Because every signal is just a shifted version of each other. Like it's an impulse response shifted in each other, and you get a different response. And from the linearity, this is where the shift invariance is. And from the linearity, it says that if you decompose this input, decompose the input into multiple different kind of versions passing through the system, and the output is just an output of this collection of outputs, add them all together. Okay. And this can be rewritten as this convolution form. Okay. So this is just a representation, more mathematically formulated. I have this collection of impulses weighted by the values. Okay. And you can apply the linearity here, and then you apply the shift invariance. So this becomes the so-called convolution. Okay. Right. Questions? Yeah. When you talk about that, they are equivalent. They are the equivalent things. If I have something that is convolution, it implies that it's a linear and shift invariant property. And if you have something that's linear and shift invariant, it must mean that there's a operation, there's a hidden edge that's the impulse response, and that they can completely characterize your system. That both are the same thing in different side of coin. Okay. All right. So this is great that we can do this. It means that in general, it's not the case, right? If I feed in signal, I get an output. I don't really know if I feed a different signal, what the output look like. It's not necessary. You don't necessarily know this. But for shift invariant system, it's very clear. If you know what happened if you send an impulse response into the system, if you know the edge, then you know everything. Then you know every input. Then you get the corresponding output. That's coming from this operation, the convolution. Okay? So it's fully determined by just knowing the impulse response. All right? So here, the operation, it looks exactly like the filtering, right? So here, basically, you have this edge, and at every location, you basically do a weighted average of the input signal, right? The weighted average of the input signal, and then you get the output. Okay, so this is essentially filters. Yes. Edge is the kind of the weights of like local window, how you apply this to the weighted average of the input values. And edge also is the output of if you're feeding an impulse response to the system, and that's your edge.
Like in the early example.
Yeah. In the early example, like edge is just a kernel, right? You just like 1/9, and then everything is 1. So basically, every pixel is kind of 3x3 window, and every pixel is 1/9. Okay, it's basically the weights applied to the input. Okay, so now with this understanding, let's try to understand this. Okay, so you have the input, and then you have a system. This is Gaussian blur. Here, the Gaussian here we can say that the edge is just the Gaussian kernel. Okay, this is just a two-dimensional things. All right, so now we need to understand, like this tells us the spatial operation, right? Basically, you have the input signal, like this is the image, and you have a weight that's linear and shift invariant that apply to local window to every pixel, local location, compute weighted average, you get the output. But how does it like why the Gaussian blur is better than the box blur, right? That we still don't know. So for that, we need to understand the frequency perspective. Okay, so imagine that you have a two-dimensional vector, right? So any vectors you have. And basically, the naive way to represent this two-dimensional vector is that you have an x component and y component. Okay, so what you do is that kind of fundamentally what you're saying is that a point P is a two numbers, and the way you represent two numbers is that you have some scale of the A1 and A2, and you have a basis. Fundamental basis that's V1 and V2. They're orthogonal to each other. Okay, so it's just like a very simple way to describe a point in 2D. Okay, so but you can also think about that, and this is just an XY. But you can also, and this is the basis of this one, and you can also represent this as the vector representation. So you have a basis vector that's just 1, 0, 0, 1, and your coefficients A1, A2. So, and this is kind of boring, right? So this is basically says that any point xy, it's when you say a point in xy location is represented by a basis and coefficient. Okay, and the reason why we want to represent this kind of similarly contrived things is that you can think about you can change the basis to represent the same thing, and this is exactly what we're going to do later on. to represent, instead of from the spatial domain to describe a data, you can use a frequency domain to describe the same thing. Okay, and the way when you view the same thing from a different perspective, so something interesting will come out. Okay. All right, so that's why we want to kind of study this. Now we have this, and you can say, if I can get the coefficients of that by just applying like inverse transform of this basis vector, right? So this is, again, kind of trivial. All right. Okay, so what's going to do? Like, what you can basically say, okay, now I want to describe the same point, but I know how I want to change the basis. Okay, and then now kind of original basis this. Maybe I rotate the basis a little bit. Like I use a new coordinate system to describe the same point. So what will happen there? Okay, so now you have you want to know the coefficient of that point, right? So now you have a new basis. You want to have C1, C2. Okay, you have the new basis C1, C2, and you want to describe this from the XY is equal to C1, C2. So similar before, it's basically XY location is essentially the C1 times U1 plus C2 times U2. Okay, so it's just way to represent this. Okay, and then you can also figure out if I want to go get the coefficient under this basis, how much U1 I need, how much U2 I need to represent the same data. And the way you do this to figure out that is trying to apply this basis vector and then take the inverse. Okay, and there's something in algebra here that if you have a basis vector that's also normal, basically orthogonal and normal vectors for unit vector for each column vectors, the inverse of this is just taking this vector, these things transpose. Okay, so it's just some basic linear algebra facts. All right, so it looks like this. Right, question so far? So this is just a refreshing that any data you can, if you find any data you represent in certain domain, certain basis, you can change the basis to describe the same data. Okay, I'm just using the 2D example to illustrate this fact. So far so good? Yes. Yeah. I'll get to that. Okay. All right. So now let's see how we can do this. Okay. Suppose I have a. So here, so first of all, I want to describe like we have this blur, but we have this question. But now I'm trying to describe. Okay, any signal can be represented by a different basis, and then later on we will connect this together. All right. So you have any signal like this, and you can describe this signal by a collection of numbers, right? Collection of like, oh, this number is f1, f0, f1, and to fn minus 1. Okay. So also you can also represent similar to the 2D case. You can also represent this as you have a basis that is for every location. You have a one half vector, and then you have scaled by the coefficients. Okay. Again, this is kind of trivial representations. Right? So this is called standard basis. So let's call E1 and E to En. But what's interesting here is that there's another basis that's very important that you can describe this into V0 and Vn. And that basis is called like sinusoidal basis. Okay. So basically what it does is that you can think about any signal can be decomposed into sinusoidal waves. And these waves have, these waves have different frequency. Okay, have different frequency. For example, you have a low frequency, zero frequency. It's just a constant values, and you have some lower frequency. Here, this is like just 1 cycle, 2 cycle, and so on. Okay. So, and these waves can also change this is the frequency. You can also change the phase. Okay, so you can also change this frequency, or can also have different phases. Okay, So the idea is that you can also describe, so these are the V, different function, different bases. And you can also describe this by a linear combination of these bases. So this is when we said, okay, image has some high frequency components and some low frequency components, okay? And when you do the homework one, what you do is that you want to apply filter to extract the low frequency component and extract the high frequency component, okay? All right, so we have these bases, and you can see, okay, if you find by finding the correct scaling, like how much coefficient and how much shift for each basis, then you'll be able to do for each basis, and then you can combine them together. Okay, so this is basically the idea of Fourier transform, right? So I have a single input x, and then I can describe by some coefficient ck, and describe by this cosine wave with certain frequency and certain shift. Okay, and then this can perfectly reconstruct the data. So the analogy what we have earlier is that instead of using the orthogonal basis, now I have this cosine waves as basis. Yes. Later on, we'll show this. Okay. The reason why you want to do this is that it provides a signal. For example, imagine that you want to do a sound wave and you want to do denoising. Okay. It's very difficult to do this in the time domain. Okay. But in the frequency domain, it becomes very easy because you have certain pitch, like, and then you can certain frequency that maybe your noise is a particular frequency, and you can isolate that very easily. So you can think about it's just a different lens of looking at the same thing. Okay, and this is kind of a great tool for doing that. Yes. Yeah, right now it's just sinusoidal way, just cosine function. Okay. All right, and then you have a normalization term here. Like let's remove that first. Okay, but this is this is not yet the full Fourier transform, right? Because this is still somewhat annoying because I have this phi here. I have this this annoying phi here because what I really want is that the basis is something fixed as opposed to that will still be able to move, right? Because this phi is moving. Okay, this phi is annoying. So we need to kind of figure out how we can get rid of that phi. Okay, so here you use some kind of high school math where you know cosine A plus B equal to this equation. Okay, I forgot what's the name of this equation is, like cosine rule or something. Okay, so once you have this, then it basically says you can decompose this into this, all right? Because now you have this guy is A and B, and just apply this equation, then you get something like this. Okay. All right. So you have a cosine term and the sine term. So now you can remove these things into this part, and now you have this these two coefficients. Okay. But I don't want to kind of represent this into two coefficients. It's kind of annoying. I want to, like, I have a basis and I have just a coefficient, right? So that's kind of become much easier to understand. So let's call this A and B, AK and BK, right? So the purpose is to really try to figure out what is the coefficients and what's the basis, okay? So we have AK and BK. So AK, again, this is just the summations of these guys doing cosine transform and the sine transform, right? But this is still not satisfactory because I have two things to keep track. I don't want to keep track of two things. So what we should do? Let's take a look at cosine and sine. So one way to think about this is that any kind of, you can use this, describe this in if I don't know whether you have learned this complex number idea. Basically, you can think about the cosine and sine. Essentially, you can think about this just a data point on a circle, right, in the complex plane, right? So this cosine, this x coordinate is a cosine and y coordinate is a sine, okay? All right, so if I want to do that, I can basically try to represent this. So here I have this this called Euler rule, Euler equations. Basically, it says that this exponential function is this cosine plus I sine omega, and the e of the minus signs is this guy, the cosine omega minus I sine omega. All right, so you know that these two things is just these two things, okay? So what you do is that you plug in this guy into this, plug in this guy into this, then this is what will happen, okay? So it's kind of become a scary term. And then like I probably don't want to kind of bombard you with too much kind of math behind this, but basically what you can show is that once you have this and you can show that some symmetry, you can merge these two terms together, okay? So once you have this, you can show that this guy is just, you can merge this thing together. Let me see. So basically the idea is that if you move, rotate in one direction is the same as a 2 pi minus the other directions. So that's the key. And then you can move this together. And then what? Okay, so I probably shouldn't talk about these too much details. But basically what I want to show you is this, okay? So once you have this, now you can represent any signal as a sinusoidal, as a kind of complex exponential on the right-hand side and the coefficients, okay? A is minus B, okay? Then then this is where we can arrive at a Fourier transform. Right? Basically, the coefficient is just a complex number of AK and minus IBK. And you can represent that as a CK, like just a CK that's a complex number. Right? Okay, so this is called inverse Fourier transform. Discrete Fourier transform basically says that I can reconstruct, I can take any signal X and I can represent that as a sum of sinusoidal waves and with some complex coefficients, right? That is inverse Fourier transform. And at the same time, you have something that's a forward Fourier transform. That is, remember that if we want to, if you have a coefficient, if I have a data, and I want to represent that same data in a different basis, and now here the basis is this guy, and the way we do this is to do the dot product between this basis and that signal, right? And that gives you the coefficients. All right. So that is the gist of like Fourier transform, right? So this is a way for you to represent any data in the spatial domain and represent that in the frequency domain. Okay, so there are a lot of math, but what is the purpose of this? Okay, so now you have let's go back to these operations. So you have input. And you have a system that produces the output. So now, remember that you have this input. This is a signal. This is a signal here. This is a convolution operation. So Gn is the convolution of these guys. All right. So now, if you say like this is the Fourier transform of this guy. Is the Fourier transform of this guy. And what you will find is that, okay, so I just plug in the first equation into the second equation. Just plugging in this Gn into the second equations. And this is what happened. Okay, plug in this guy. I'm not doing anything. I just say the Gn is a convolution, basically the filtering between the input and our kernel, that's weight, the H. This is the convolution operation. I just plug in, and I want to know what's the Fourier transform of the output. Okay, so you do some massage because there's linearity, so you can swap these two terms, And now you have these things, and you do some kind of change of numbers. Use the p to represent n minus m, and so on. And what you'll do is that you can decompose these two terms into this. And now, because this guy is this guy does not depend on the p, then you can merge this term. You can move these terms the other side. So you can work on the derivation later on yourself. But what I'm going to show here is the following. It says that the following. So this guy, the Fourier transform of the output signal is the Fourier transform of the input signal multiplied by the Fourier transform of the system, okay, of the filter. Okay, so this is called, like, basically this relationship is called convolution theorem. Okay, so why you want to do this? It basically tells you exactly what does it mean to have applying a filter on top of a signal. What it actually is doing is that it's trying to change the frequency domain information of the input signal by this frequency domain of the filter. Okay, so we can understand what it's actually doing. Okay, so here's what it looks like. If I have an input signal, that's the input signal, and you apply a Fourier transform, basically decompose this into frequency coefficient of frequency. So basically what it does is that at center is a low frequency constant, zero frequency, and you go to the right and go to the left. These are the coefficients that are higher and higher frequency. Okay, so this is the frequency information about the input signal. Okay, so if you take these sinusoidal waves and multiply by these coefficients, then you get back to the original signal. So it's the same data, but a different perspective. Okay, so now based on this, so this is the different frequency components. Okay, and then you can see if we apply the Fourier transform on the system, that's the filter weights we have, we get something like this. Okay, in this case, it's a Gaussian filter. So what it says is that it basically says the following: like, in the end, output is going to be the multiplication of this guy times this guy for every location. So what is this guy doing? It's basically saying that if the coefficient, if the frequency is low, then you have a high value. Okay, if the frequency is higher, then you have a lower value. It's trying to suppress the high frequency signal. Okay, suppress the high frequency signal, and this what and the output of this, it will look like this. Okay, so the output is the input frequency representation multiplied by this guy. Okay, so this reveal that this understanding help us to understand that given any inputs, you can decompose this into represent that same data in the frequency domain. And if you have a kernel, you have a filter represent in the frequency domain, that this guy tells you that operation, that special operations, like for example, take the center plus weighted sum of the nearby points, that tells you that this is actually doing suppressing the low high frequency components. Okay. All right, so this is one aspect of why frequency domains could be very useful, right? Because here you can see that it's trying to suppress these things. And another aspect is that sometimes if your kernel is large, if you apply this in the operation in the spatial domain, it's slower. And you can, because they are equivalent, right? Instead of using this in the frequency domain, instead of using this in the spatial domain, what you could do is that you take an image or any signal, you first convert that into frequency domain, and convert this your filter in the frequency domain, multiply them together, and then do the inverse transform, and this will be faster. Okay, so especially you have a large filters you want to compute, then this relationship tells you that there's another way of doing linear filters. Okay, so this is what I said. You can, instead of doing this system directly in the spatial domain, you can also think about you compute the frequency domain first, and then once you get, and then this multiplication is trivial, and then you do the inverse frequency transformation to get back to the original data, to get back the output. And this output is to be exactly the same. Yes. The middle of that, it's not really a distribution. It's just the middle one is indicates how much low frequency components you have. And throughout if you go to the right and left, it's basically higher and higher frequency components. So there are multiple different applications. For example, one is that to understand this better. Another one is compute this faster. Yet another one is that if you have a signal, because most of the signals are typically lower frequency, that they have a stronger frequency components. So what you could do is that you take the image, any signal you have, convert it into frequency domains, and then you will be able to compress this more effectively, because you know that now you concentrate this in the low frequency component, you can drop a lot of high frequency components. And this is exactly the basic principle of JPEG and all these image and video compressions. Okay, so by just looking at providing a new way to look at the data, and then you can do a lot of things. Yes.
Original domain is just a 2D presentation.
Yeah, 2D representation is just the first pixel is 1 and the second pixel is 1 and so on. 1 half vector. That's how you represent a 2D data. It's also the same, right? So if you have n pixels, say 100 by 100, you have 10,000 of them. Then frequency domain is also have 10,000 of them. Okay, it's just that like just if you have 2D data, you represent this in the 2 dimension, 2 vectors, and if you have a 10,000 dimension, then you have a 10,000 vectors. Okay, basis. Sorry. Okay, so let's get back to this box filter things. Okay, so this is now we can try to understand why box filter is not great. Okay, so you have a box filter, and this is a box blur, and what you will do is that you apply a DFT, the Fourier transform, and this is the frequency information. So now instead of 1D, that's so here the center here is you can see the a bright yellow spot. That's your coefficient of the low frequency components, like the overall strength. So you can see that it's very strong there, like it's because most images are smooth. Okay, so the low frequency component is very strong, and along the x-axis, that indicates how much horizontal frequency you have in the image. Okay, and if you go to the right more, it means that higher and higher frequency. So same thing for the vertical ones. If you go up, that's the basis for the coefficient for the basis of this vertical frequency. Okay, and you can also have certain like frequency that's horizontal, this vertical, this kind of slanted slice of the sine waves. Yes.
You obviously know what you want that.
Right. So if you want to do this apply a Gaussian blur in the F frequency domain, this is what we'll do, right? So we would first compute the DFT of the input image, and then we'll compute the DFT for the signal. So for the for the blur kernel. So the DFT, okay, so I didn't have slides for that. Basically, the way you do this is that like it's just like a same concept as trying to find the coefficients, right? So this is basically, you can think about DFT, it's just a coordinate transformation, okay? So the way we do the coordinate transformation in 2D is just to take a basis vector and then do the dot product between the data and the basis vector. And same thing here. Okay, those every data point here is just you take the basis vector, do the dot product between the basis vector and the data. Okay. The entire image. You are doing therefore the entire image. So in the 2D case, like think about the image is just 10,000 dimension. But we know in 2D case, it is the same concept. In 2D case, you have a basis vector, you have a new basis vector. In order to find the coefficients of the same data expressed in the new basis vector, what you do is that you take the basis vector, do the dot product between the basis vector and the data. Okay. Okay. So now in this box filter, what we do is that if you take the box filter and if you apply the DFT, what you find is this. That this is the frequency transform of the box filter. So there's a name for that. It's called sinc function. So what happens here? You can see that the output of this is the output of the box filter is going to be. You look at this. It looks like this. Okay. So what happened here? So this box filter, when the output of the Fourier transform of this filter output is this guy, and it's the same as the multiplication of this guy times this guy, pixel-wise multiplication, element-wise multiplications, right? So you can think about box filter. What box filter is doing is that it's trying to modulate the frequency magnitude of the input. But the way they modulate this is it indeed keep the low frequency intact, like it has a low pass filter, but they have this kind of weird artifacts where they have this they still let some of the high frequency components pass, and therefore you see this kind of artifacts here. Okay. All right, so this is box filter. To understand that, okay, so this is the ringing artifacts is coming from because the filter itself in the frequency domain, you reveal that it's not really doing the high frequency, removing the high frequency. Okay, if you look at the Gaussian blur, you look at the Gaussian filter, this is what it looks like. Okay, so it has a very nice like low pass component. Basically says that our output is going to be this guy times this guy. Okay, element-wise multiplications, and you can see that it has a smooth decay over the high frequency component. For the high frequency component, you will suppress that, and then it doesn't have this kind of ringing artifacts there. Okay, so once you multiply these two, you can also think about the output is just going to be this guy. All right, so it's actually trying to remove all this high frequency informations on the from the input image. Okay. Question about this. So this is why we go all the way to describe the discrete Fourier transform so that we can understand what's going on here. Yes. So there are, like, conceptually, it's understanding what the filter is doing. For example, if you have a filter, you want to understand what it's actually doing, because for spatial domain, it's just doing some mechanics, like doing some weighted average, right? But frequency domain, you understand that, okay, is it trying to isolate a particular frequency band or do something, right? This is understanding part. And for computation-wise, if your filter is larger, because you have fast algorithm for doing this DFT, it's called FFT, fast Fourier transform. So you have this faster algorithm for doing this Fourier transform and inverse transform. So if you want to convolve, if you want to filter an image with a large filter, doing this in the frequency domain is faster. Yeah. Yeah, reduce. You can see that these are low values, right? So you can basically trying to kill these high frequency components. Yes.
What happens if you reverse it? That you kill the low frequency?
Yeah, exactly. This is exactly what you do in the Homo 1. Like you apply, when you take an image, apply a Gaussian blur, then you will remove the low frequency. You will remove the high frequency component. If you take the original image minus that remove one, then you essentially get a high frequency component. Okay, and so that's why you kind of take one image, apply a low pass filter, Gaussian filter, get a low frequency, take another image, apply the high frequency, and then can add up together to get illusions. Yes.
Is there anything better than a Gaussian?
Ideally, what you really want is to isolate the low frequency, right? Have a precise control, but typically you don't have that. If you want to have a perfect filter, then there's some theory about the kind of, if you want to have a finite support in the frequency domain, then your spatial filter need to be infinitely large. So you need to have certain kind of decay, like Gaussian filter. Okay. So filter design is also a kind of important topic. All right, so let's see what happens when you increase the kernel size or increase the sigma, like basically more blur in the spatial domain. Okay, so here you can find that if you increase the blur, you will remove more and more high frequency domain, high frequency signal. Okay, so you have a more and more. You can see that the frequency representation gets shrink, right? If you have a more blur and you get shrink, if you have a smaller blur, you get wider. Okay, so this is how you can understand that if you apply a Gaussian blur that has a larger standard deviation, it corresponds to it corresponds to controlling how much frequency you want to remove. Okay. Okay. Okay, so I want to stop. Maybe I want to stop here. Any questions about this? Right. So this is the spatial frequency. Spatial filters can be understood by just spatial operations, but you can also understand this from the frequency perspective. Okay. So in practice, what you do is that imagine that you could potentially do this, right? You can potentially do this Gaussian filter by just discretize the Gaussian filter, Gaussian function, basically pick this one. But there's a problem, right? In this case, you don't really get to the, if you apply this Gaussian filter, apply another Gaussian filter again, in the continuous space, you have a very nice property that it will just get a larger Gaussian kernel. Okay, so imagine that you have if you want to have I don't know, even Zoom meeting in the background blur, like you have a background blur, and that's very blurry background, and that's a very large Gaussian filter, right? So having this property of applying two Gaussian blurs and equals the larger, achieve the same effects of applying a larger Gaussian blur. And because applying a smaller Gaussian blur is computationally much cheaper. So typically you want to apply the Gaussian blur sequentially to achieve the same effects. Okay? So, but this one, it works only in the spatial domain. But now in the practical consideration, it doesn't really work for if you use a discretized Gaussians. Okay, if you use a discretized Gaussian, if you repeatedly apply the Gaussian blur, so the yellow curve is a continuous Gaussian function, but blue curve is the discretized version. So you can see that is some approximation, right? So some arrows here. Okay, so typically what you want to do is to use something that's called binomial filter that looks like this. It's basically take one and take a two at center, one and one at the surrounding, and divide it by the normalized them. Okay, so if you take this binomial filter and then you apply this multiple times, the idea is that binomial filter come out with itself is also binomial filter. It looks like this. And over time, you'll see that it gets you a very good approximation. Okay, so this is if you want to implement the Gaussian filter, this is the way to go. Okay, so you can see that if you larger and larger filter, you get more accurate results. Okay. All right, so there's some practical considerations. For example, this is a Gaussian filter. It's a binomial filter, but in a 2D domain. Okay, so in the binomial filter, in this case, but I don't want to, if I want to apply this in the image, but I don't want to apply in the 2D case, it's more computationally expensive, right? So, but these filters can be decomposed into two filters, two 1D filters, okay? So on the left-hand side, I need to compute this in the 3x3, so I need to compute 9 operations. On the right-hand side, I only need to have 3 and 3, that's just 6, okay? But you can think about if you have a larger filter size, then this will be even cheaper, okay? So the idea is that you can achieve the same 2D blur by first applying a 1D blur horizontally, followed by a 1D blur vertically. Okay, so this is called separate filter. Okay, so here's what it looks like. If you take an image and you want to apply the 2D blur, what you do is that you first apply the blur along the x directions. So you apply the blur, the x direction, so you can see that it sort of looks like a moving. And then you take this input image take this as an input image and apply a blur along the other directions. Apply the other directions, and you get you get output. So this result is mathematically equivalent to the result of directly apply a 2D filter. Okay, because the filter can be composed together. Okay, so this is all I have to say about filters and in the spatial domain and the frequency domains. So next lecture, I will not be here. The TA will talk about how we can use this filter to do downsampling. That this is important application of doing downsampling, and then do the how do you do the pyramid blending and so on. So then more application in the image filters. Okay, right, thanks. Yes. Yeah, so I asked TA to annotate the corresponding lectures with the textbooks. There are textbook that has more detailed information than. Yeah. Yeah.
Like earlier, like 30x30 kind of kernel, where like I think it was like 1/9 all the values.
Yeah. This I'm applying the Gaussian filter, so yeah, separately. So basically it says that this kind of blur filter can be implemented with this 1D filter, and this is kind of faster to do this.
Because like I was the Gaussian thing when you sort of map, how does that get into the information?
Can you say that again?
Like so. It's like I remember because like when you did the show like the geography and everything.
Yeah.
How does that like translate to like like multiplying by and then vector.
Oh, this one?
Yeah.
So this guy is just the pixel wise. You can see about these are just a 2D array of numbers. And just multiply this by this. Like this is the same, like 2D, like pixel wise, for every location you use multiplication. Element wise multiplications. It's not matrix multiplications.
Oh,
Right. So it's actually it's very simple. Like, so you can see that in the middle is high value. So especially keep the high value intact and suppress the low values. Yep.
I know being in a layer,
Mhm.
that is just like a filter, element-wise convolution.
Yeah.
In this case, the signal is not a pixel, but an entire image.
The signal, signal is the entire image.
So, I mean, the 100 by 100 image has a 10,000 dimensional basis.
Yeah. It's an image you can see, but it's a point in that 10,000 dimensional space.
But the kernel is still the small one.
Right. So
You can
you can say about that that's in the spatial domain, like image, and then you have a kernel to operate on that top of the image is just a 3x3 kernel or kind of 5x5, 8x8, it's local window operations. And that's what convolution neural networks, that the basic components that.
So the image and kernel can be transformed to the same frequency domain.
Right. So so this is what happened, like image, and they apply this. First, look at the image representations from a frequency domain perspective. They're describing the same data. Like instead of thinking about this in the image space, you think about this in the frequency space. And the idea is that the convolution in the spatial domain is equivalent to frequency domain multiplications.
And that is faster.
Yeah, it can do faster. Yeah, good. Hey. Okay, so I'll check with the TA and make sure that they upload this.
Okay.
Yeah.
There's an inconsistency. It's like what sort of questions would you ask? Like, is it
Oh.
in the blanks or MCQ or like
MCQ? What is that?
what sort of question types can we expect?
Oh, okay. In the midterm. So we will talk about a little bit about some of them will be coming from the homework assignments, the programming assignments, and some of them will be more like a conceptual questions.
So is there any like calculation questions like?
Yeah, there'll be some basic, like I ask you to apply this, or I ask you to have different filters and see how can match these things. Mostly conceptual understanding. Yep.
Also have a question on the midterm.
Yeah.
Like the proofs that you do, will those be on like the midterms or like is it?
Probably not. Like
It's like how
probably.
to deal with Python, right?
But I think that there's something, for example, I will probably ask, I don't know, like some basic idea of filtering, right?
Yeah.
So and the frequency perspective, but I probably won't test your, like you can memorize the derivations.
Yeah,
right?
yeah.
That derivation is kind of the background material to assure you that
Yeah,
it's
yeah.
actually there's a derivation that it's not coming out of nowhere,
Yeah,
right?
exactly.
Like because people a lot of time people just kind of when they first learn Fourier transform, the first thing they learn is that this giant like
Yeah.
random equations, but it comes from the fact that you do the change of basis, right? You do the then you have this new basis that's sinusoidal waves, and then you have some steps to arrive at Fourier transform.
Okay.
But that probably not going to test though. Yeah.
Thank you.
Yep.
Oh, also, my mom also works at Reality. I like
Oh, okay. Oh,
Yeah,
cool.
that's nice.
Yeah. That's awesome.
Thank you.
Yep. Thank you.
I test something.
Oh yeah, no problem. Yeah, no problem.
Thanks.